October 12, 2025. Pan-STARRS Observatory, Hawaii. The automated survey system flagged an anomaly in the trajectory of 3I-ATLAS, the third confirmed interstellar object to enter our solar system. The deviation measured 0.04 astronomical units, roughly 6 million kilometers off the predicted path. NASA's Jet Propulsion Laboratory ran the calculations 3 times. Each analysis confirmed the same result. The object had altered course without any detectable external force. ESA's Gaia satellite provided independent verification. The Near-Earth Object Coordination Center cross-referenced the data. Every model agreed. 3I. ATLAS was no longer following the trajectory that gravity alone should produce. The object was small, approximately 200 meters across, traveling at 72 kilometers per second, dim enough that most telescopes struggled to track it. Yet, something about its motion defied the fundamental equations that govern every other body in the solar system. Dr. Michio Kaku, theoretical physicist at City College of New York, called it a potential Rosetta Stone for interstellar propulsion. NASA's public statement used one word: anomaly. Their internal classification told a different story. March 19, 2024. The ATLAS Telescope Array Asteroid Terrestrial Impact Last Alert System detected an object moving through the outer solar system at a velocity that immediately separated it from everything in our catalog, 72 kilometers per second. That number matters. Comets from the Oort cloud travel at 20 to 30 kilometers per second. Near-Earth asteroids reach 40 at most. But this object moved with kinetic energy that spoke of origins far beyond the Sun's gravitational reach. The trajectory was hyperbolic, an open curve with no return path, no closed orbit. The geometry alone confirmed what only 2 other objects in recorded history had demonstrated. 3I-ATLAS came from interstellar space. The first visitor, Oumuamua, arrived in October 2017. Its elongated shape and unexpected acceleration ignited years of scientific debate and popular speculation. Some attributed its motion to outgassing frozen gases, sublimating as the object warmed near the sundae. Others proposed more exotic explanations. The second, Comet 2I, Borisov, passed through in August 2019 and behaved exactly as centuries of cometary science predicted. It outgassed visibly, developed a tail, brightened as it approached perihelion. A textbook interstellar comet, strange only in its origin, not its behavior. 3I. ATLAS was catalogued as the third. Initial observations suggested it would follow Borisov's pattern, a frozen body from another star system heating and sublimating as our sun's radiation intensified. Spectroscopic analysis in April 2024 detected faint traces of water vapor and carbon monoxide chemical signatures consistent with cometary ice. The object appeared dim, roughly magnitude 22, visible only to the most powerful survey telescopes. NASA's Horizons system, the computational framework that predicts the positions of every tracked object in the solar system, calculated 3I, ATLAS's path, using standard gravitational mechanics and estimated outgassing pressure. For 6 months, the predictions held. Then the deviations began. By late September 2024, high-resolution imaging from the James Webb Space Telescope revealed the first anomaly. The object was dimming when it should have been brightening. October 15th through November 30th, 2025. The world's major astronomical facilities turned their attention to 3I-ATLAS. The Atacama Large Millimeter Array in Chile measured thermal emissions across multiple wavelengths, constructing a temperature map of the object's surface. The Subaru telescope in Hawaii captured photometric data, precise measurements of how the object's brightness changed over time. The European Southern Observatory's Very Large Telescope in Chile analyzed its spectral composition with unprecedented resolution. Every new dataset introduced another contradiction. Photometric analysis revealed a brightness curve that was smoothing over time. Natural objects in chaotic rotation produce irregular light curves. brightness fluctuating as different surface areas with different albedos rotate into view. Asteroids tumble. Comets wobble. 3I. Atlas's light curve was becoming more regular, a sine wave smoothing toward predictability. Dr. Avi Loeb, Frank B. Baird, Jr., professor of science at Harvard and chair of the astronomy department, published preliminary findings in the Astrophysical Journal Letters, stating that the photometric behavior is consistent with rotational stabilization, a process not typically observed in natural interstellar objects of this size. Thermal imaging presented another challenge. The object's surface temperature registered approximately 4 degrees Kelvin above the cosmic microwave background, warmer than ambient space, but far too cool for active sublimation or any exothermic chemical reaction capable of producing thrust. Where was the excess heat coming from? 3 competing hypotheses emerged. None of the models matched the observed trajectory. The object was accelerating slightly, but measurably in directions that required forces greater than solar pressure, and in vectors inconsistent with random outgassing. On October 3, 2025, the James Webb Space Telescope captured a spectral anomaly during a scheduled observation pass. A brief pulse in the near-infrared band. Duration: 4.2 seconds. The frequency of the pulse: 1,420 megahertz. The hydrogen line. Hydrogen, the most abundant element in the universe, emits and absorbs electromagnetic radiation at a precise natural frequency, 1,420.405 megahertz. This transition between hyperfine states in the hydrogen atom is so universal and unmistakable that scientists have long theorized it as the most logical frequency for interstellar communication. Any civilization capable of radio astronomy would recognize it immediately. SETI's Allen Telescope Array, located at the Hat Creek Radio Observatory in Northern California, was directed to cross-reference the observation. The timestamp didn't align with any detection in their continuous monitoring data. The pulse appeared in Webb's infrared sensors, but not in dedicated radio telescope arrays pointed at different regions of sky. It did not repeat during the subsequent 72 hours of intensive monitoring. NASA's assessment, distributed internally among project scientists: spectral feature detected at hydrogen line frequency, origin undetermined, possibility of instrumentation, artifact under investigation. The object's monitoring priority was elevated to continuous high-interest observation, a classification reserved for near-Earth objects with potential impact trajectories and historically significant targets of scientific importance. Translation: something unusual was occurring, and no consensus existed on what it meant. Comets obey predictable thermodynamics. As solar radiation heats their surface, volatile ices sublimate transition directly from solid to gas, creating visible outflows that scatter sunlight. The closer a comet approaches the sun, the brighter it becomes. 3I. Atlas was doing the opposite. Its luminosity was decreasing. No dust tail appeared in visible wavelengths. Infrared observations showed thermal emissions far below what sublimation models predicted. Dr. Michelle Bannister, planetary astronomer at the University of Canterbury, who specializes in trans-Neptunian objects, noted in a NASA teleconference that the object's thermal profile is inconsistent with active outgassing at this distance from the sunday. The language was careful. The implication was not. Radar observations from the Goldstone Deep Space Communications Complex added another puzzle. When radio waves were bounced off 3IATLAS to map its surface and rotation, the return signal showed something unexpected. The object wasn't tumbling chaotically like every natural asteroid and comet ever studied. Its rotation was stabilizing. Natural bodies shaped by collisions and gravitational chaos spin irregularly, their rotation axes wobbling, their angular velocities fluctuating as asymmetric mass distributions interact with solar radiation pressure and internal stresses. 3I. Atlas was evening out its spin, gradually reducing rotational wobble as if correcting for imbalance. The data was subtle but consistent across multiple observation windows. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, later wrote in a mission summary report that the rotational behavior is atypical for objects of this size and composition based on current understanding. Again, the language was diplomatic. By early October 2025, JPL's orbital prediction models, recalculated every 6 hours, using the latest telemetry, began showing acceleration vectors that didn't fit. Solar radiation pressure exerts a measurable force on objects in space. Photons carry momentum, and when they reflect off a surface, they transfer that momentum to the object. For small, light bodies with high surface area to mass ratios, this pressure can measurably affect trajectories. NASA's models accounted for this. They also accounted for gravitational perturbations from Jupiter, Saturn, and the Sunday. They included estimates for asymmetric outgassing directional jets of sublimating gas that can create small thrust forces. If the object's composition was heterogeneous concentrations of volatile ices distributed unevenly across its surface, then outgassing could occur in directional bursts rather than uniformly. This would create small rocket-like thrust forces pointing in specific directions. ESA's Rosetta mission to Comet 67P, Churyumov-Gerasimenko, documented precisely this behavior. Jets of gas and dust erupted from specific surface features as solar radiation heated localized pockets of ice, creating measurable forces that altered the comet's rotation and trajectory. The model fit some of the data. The trajectory deviations were small enough to be consistent with outgassing forces, and the lack of a visible dust tail could be explained if the outgassing was primarily composed of transparent gases rather than reflective dust particles. But thermal observations showed no hotspots, no localized regions of elevated temperature where active sublimation should concentrate. The object's thermal profile was remarkably uniform. If 3IATLAS were not a solid monolithic body, but instead a loosely bound aggregate, a rubble pile held together by weak self-gravity, or even a thin sheet of material with extremely low density, then solar radiation pressure could exert disproportionate force. The concept was not unprecedented. Scientists had proposed using light sails' ultra-thin reflective sheets for interstellar travel precisely because photon pressure, though weak, accumulates over time and distance without requiring fuel. If 3IATLAS had a surface area to mass ratio significantly higher than typical asteroids, radiation pressure could explain the anomalous acceleration. But radar observations suggested a relatively compact object. The echo delay timing indicated solid structure, not a diffuse cloud of debris. And the object's rotation should have been more strongly affected by radiation pressure. If it were truly low density, it should have been spinning up, not stabilizing. This hypothesis was rarely stated explicitly in peer-reviewed literature, but dominated private discussions among researchers. If an object from interstellar space exhibited trajectory changes inconsistent with natural forces, rotational stabilization, anomalous thermal properties, and spectral pulses at frequencies associated with potential communication, the question had to be asked, could the object be engineered? Dr. Michio Kaku, speaking on the Star Talk podcast in late October, articulated what many hesitated to say publicly. We have an obligation as scientists to consider all hypotheses consistent with the data. If natural explanations require increasingly elaborate assumptions, if we must invoke special compositions, unlikely geometries, and multiple coincidental factors, then we must at least evaluate the possibility that what we're observing is technology. Not because we want to sensationalize, but because excluding that possibility without evidence is intellectually dishonest. NASA's internal briefing documents, portions of which were later released through Freedom of Information Act requests, used language that acknowledged the ambiguity. Object exhibits non-gravitational acceleration. Mechanism undetermined. natural and non-natural hypotheses under evaluation. The phrasing was precise. Non-natural did not mean artificial. It simply meant not explained by currently understood natural processes. But the implications were clear. On October 18th, the upgraded Arecibo successor system, a distributed array of radio transmitters in Puerto Rico, transmitted a radar pulse toward 3IATLAS and analyzed the return echo. Radar astronomy works by bouncing radio waves off distant objects and measuring the reflected signal. The timing reveals distance. The Doppler shift reveals velocity. The echo's characteristics reveal composition and structure. Solid ice or rock produce clean reflections. Porous material scatters the signal. Metallic surfaces create strong, sharp echoes. The 3IATLAS echo contained unexpected harmonics frequency components that suggested internal structure with varying density layers. Dr. Patrick Taylor, who oversaw the observation, described the result in a NASA technical report. The echo profile is atypical. The delay pattern indicates density stratification inconsistent with homogeneous rocky or icy composition. On October 21st, 3IATLAS brightened suddenly, increasing in apparent magnitude by 0.3 for 11 minutes, then returning to baseline, a 30% increase in reflected light. No outgassing plume appeared in any wavelength. No thermal spike accompanied the event. The object simply became more reflective, then stopped. The Deep Space Network, NASA's array of large radio antennas used for communicating with distant spacecraft, detected faint electromagnetic anomalies during routine tracking sessions. Not signals exactly, but phase shifts in the carrier wave, as if something were resonating at specific radio frequencies. The data was subtle enough to be dismissed as interference, but it was persistent enough to be logged. By late November, the scientific community was divided into three camps. The first maintained that natural explanations, though currently incomplete, would eventually resolve the anomalies. They cited the history of astronomical mysteries that seemed inexplicable until better models emerged. They pointed to Oumuamua's acceleration, initially baffling, now tentatively attributed to outgassing hydrogen ice. The second camp argued that the accumulation of anomalies exceeded the threshold of coincidence. Every natural explanation required multiple assumptions: special composition, unlikely geometry, atypical outgassing, anomalous internal structure. When every data point required a separate ad hoc explanation, the model itself became suspect. The third camp said nothing publicly, but intensified observation efforts. Dr. Sarah Seeger, astrophysicist at MIT, who pioneered methods for detecting biosignatures in exoplanet atmospheres, summarized the tension in a Nature comment piece. Science progresses by assuming natural explanations first. But we must recognize when that assumption becomes a bias. If the simplest explanation, consistent with all the data, is that we're observing something we've never encountered before, then our responsibility is to investigate that possibility rigorously, not dismiss it reflexively. The debate intensified as 3IATLAS approached perihelion, its closest point to the Sunday. December 8, 2025. 3IATLAS reached perihelion at 1.1 astronomical units from the Sun, roughly 165 million kilometers, just beyond Earth's average orbital distance. This was the moment of maximum solar heating. If the object were a typical comet, this would be the point of peak activity, maximum outgassing, maximum brightness, maximum cometary behavior. NASA's Parker Solar Probe, designed to study the Sun's corona from extreme proximity, was conducting a data relay transmission when its radio frequency instrument suite detected an anomaly. A high-frequency electromagnetic burst. Origin direction, consistent with 3IATLAS's position. Duration, 370 milliseconds. The signal was strong enough to saturate the probe's receivers, triggering automatic gain reduction, a safety protocol that prevents sensitive electronics from being damaged by unexpectedly powerful signals. The probe's data was relayed to the Deep Space Network and forwarded to JPL for analysis. Dr. Joseph Lazio, chief scientist for NASA's Interplanetary Network, led the initial assessment. What the team found stopped the analysis process entirely. The burst contained structure, not random noise, not the chaotic static of natural radio emissions from solar flares or magnetospheric interactions. Pattern. The amplitude modulations, variations in signal strength, occurred at intervals that corresponded to prime numbers: 2, 3, 5, 7, 11, 13. Prime numbers have no natural periodicity in electromagnetic physics. Pulsars emit rhythmic signals, but their timing reflects rotation rates and magnetic field structures' physical phenomena. Magnetars produce bursts, but their frequency distributions follow power laws determined by magnetic reconnection physics. Prime number sequences are mathematical abstract constructs that have no inherent physical manifestation. They are, however, universal to any intelligence capable of mathematics. The concept is simple. If you want to send a signal that cannot possibly be mistaken for natural phenomena, encode it with mathematical properties that nature doesn't produce. Prime numbers are recognizable to any civilization that has developed arithmetic, regardless of language, biology, or sensory apparatus. ESA's solar orbiter, positioned on the opposite side of the Sun from Parker, detected the same burst 4.6 seconds later, exactly the light travel time between the two spacecraft's positions at that moment. The delay confirmed two facts: the emission was real and it propagated at light speed. But a critical question remained: was 3IATLAS generating the signal or merely reflecting it? Dr. Andrew Simeon, principal investigator for Breakthrough Listen, the most comprehensive SETI program ever undertaken, analyzed the spectral characteristics. The signal's frequency profile contained harmonics consistent with reflection rather than transmission. When electromagnetic radiation reflects off a surface, it picks up characteristic phase shifts and harmonic distortions based on the reflecting material's composition and geometry. The Parker data showed those signatures. It's possible, Simeon stated in a closed briefing later summarized in declassified meeting minutes, that the object is functioning as a passive reflector, essentially a mirror bouncing back a signal transmitted from another source. From where? No terrestrial transmitter operated at that frequency range. No satellite in any catalog. No deep space mission operating in that region. SETI's continuous monitoring had detected no corresponding transmission from any direction in the sky. If 3IATLAS reflected a signal, the source remained unidentified. 6 days later, the trajectory changed again. This time, the deviation was unmistakable. JPL's Horizon system calculated a delta V change in velocity of 0.8 meters per second. Small in absolute terms, a human walking pace, but far beyond what any natural force could produce at that distance from the Sunday. More significantly, the new trajectory vector pointed the object out of the ecliptic plane, the relatively flat disk in which planets orbit, and toward interstellar space. The direction was specific. If projected forward for thousands of years, the new path would carry 3IATLAS toward a region of sky near the constellation Cygnus, passing within 10 light-years of the star Kepler 452, a Sun-like star with a confirmed terrestrial exoplanet in its habitable zone. Coincidence? Almost certainly. But notable, Dr. Davide Farnocchia, navigation engineer at JPL, who specializes in predicting near-Earth object trajectories, ran simulations testing every known mechanism for producing such a maneuver. Solar wind pressure, insufficient by a factor of 50. Micrometeorite impacts, statistically negligible at that distance from the asteroid belt. Magnetic field interactions with the solar wind, too weak for non-magnetic or weakly magnetic materials. Asymmetric outgassing from newly exposed volatile pockets. Possible, but no thermal or spectroscopic evidence of gas release appeared in simultaneous observations from multiple instruments. If I didn't know better, Farnokia wrote in an email to colleagues later cited in a Science magazine article, I would conclude that something aboard that object executed a course correction. NASA's public statement, released December 15th, described the event as a trajectory anomaly requiring further analysis to determine contributing factors. Privately, senior mission scientists acknowledged the language was chosen for its ambiguity. One researcher, speaking on condition of anonymity to the New York Times, stated simply, "We can't say it's artificial because we can't prove it. But every natural explanation we've tested requires assumptions that are individually plausible but collectively improbable." If you're fascinated by mysteries grounded in real data, subscribe to Space Files for more evidence-based investigations into the cosmos. February 20th, 2026. 3I, ATLAS crossed the orbit of Mars, moving outward at 71.4 kilometers per second. Its trajectory now carried it permanently away from the Sun, accelerating as the solar system's gravity weakened with distance. By mid-year, it would pass Jupiter's orbit. Within 5 years, it would cross the heliopause, the boundary where solar wind gives way to interstellar space. Within a century, it would be light years away, traveling toward a region of the galaxy humanity will not reach for millennia. Every major observatory capable of tracking faint objects monitored its departure as long as instruments allowed. By late March, 3I, ATLAS had faded to magnitude 26, detectable only by the largest ground-based telescopes under perfect atmospheric conditions and by space-based observatories with extended exposure times. The data archive remained active. Thousands of files collected by JPL, the James Webb Space Telescope, ESA's Gaia mission, the Atacama Large Millimeter Array, Subaru, the Very Large Telescope, SETI observatories, and university research groups worldwide continued circulating through analysis pipelines. Peer-reviewed papers appeared at a steady pace, dozens published, dozens more in review. Dr. Michelle Bannister co-authored a study in the Astrophysical Journal proposing that 3IATLAS was a fragment ejected from a planetary system during a catastrophic collision, perhaps two icy bodies shattering in a high-velocity impact billions of years ago. The fragment's unusual internal structure, the paper argued, could create atypical thermal and reflective properties as different materials sublimated at different rates. The model fit portions of the data. It struggled to account for the trajectory deviations and the rotational stabilization. Dr. Avi Loeb published a competing hypothesis in the Astrophysical Journal Letters, suggesting the object could be a derelict artifact, not actively controlled, but retaining residual functionality. Ancient solar panels or magnetic sails, degraded over millions of years but still capable of weak interactions with radiation or magnetic fields, could produce small thrust forces that mimicked deliberate propulsion. The model was speculative but mathematically consistent with observations. NASA's official position, as stated in the March 2026 Near-Earth Object Program Status Report, remained unchanged. Object 3I ATLAS exhibits anomalous characteristics requiring continued observation and analysis. Insufficient data exists to conclusively determine composition, structure, or origin. Both natural and artificial hypotheses remain under evaluation. The spectral pulse at 1,420 MHz was classified as unresolved spectral feature of undetermined origin. The perihelion burst was cataloged as transient electromagnetic event, source unidentified. The trajectory changes were documented as non-gravitational acceleration, mechanism unknown. Dr. Michio Kaku, speaking at the World Science Festival in April 2026, offered a perspective that resonated across disciplinary boundaries. The history of science is a history of discovering that we were wrong about fundamental assumptions. We thought Earth was the center of the universe. We thought our galaxy was the entire cosmos. We thought space was static, not expanding. Every major revolution in understanding came from accepting data that contradicted our models. 3I. Atlas is teaching us humility. Whether it's a bizarre natural object or something else entirely, it's showing us that the universe still has the capacity to surprise us and that our equations are incomplete. As of late 2026, 3IATLAS remains in NASA's small body database as an interstellar object exhibiting unresolved anomalies. Its composition uncertain, its origin somewhere beyond our solar system, from a stellar neighborhood we may never identify. Its purpose, if purpose is even the correct concept to apply, unknown. And somewhere beyond Jupiter's orbit, beyond the scattered disk of comets, beyond the heliopause where solar wind fades into the interstellar medium, it continues outward, silent, dim, and moving with a trajectory that doesn't quite match what nature alone should produce. What we know, something came from interstellar space, behaved in ways our current models cannot fully explain, and departed along a path that appears deliberate. What we don't know, whether that appearance is real or illusion, whether we witnessed something extraordinary or simply encountered the limits of our understanding. The answer, if there is one, travels with it receding at 71 kilometers per second, carrying data we collected but may not yet know how to interpret. And in observatories around the world, researchers continue analyzing the archive, searching for patterns, testing hypotheses, waiting for the next interstellar visitor, because there will be another. The galaxy is vast, and the space between stars is not as empty as we once believed. If evidence-based space mysteries and real scientific anomalies intrigue you, subscribe to Space Files for more investigations into the cosmos's unexplained phenomena.